Hey everyone, it's Dr. C here with All This Science. Today I'm doing a short special video episode where I want to discuss buffers in terms of chemistry, in terms of the fact that students often have issues with buffers. They're really not that tricky. Once you see this short hockey story analogy, you will be an expert at buffers. So, a buffer resists pH changes. This is important in biochemistry when we're talking about maintaining the blood at a slightly alkaline level. We're talking about what's happening in your guts with the gastric juices. We're talking about proteins and enzymes, fermentation, and even in coloring fabrics, the way that dyes will be stuck to the fabrics. So that is an array of examples where buffers are important in everyday life. So just as buffers resist pH changes, a hockey goalie, resists goals, especially against him or her. So we have a picture of a goalie here. We have a typical buffer system made up of acetic acid. I shorten it to HAC, where the AC refers to the acetate, CH3COO-, and the H plus attached to it. We'll prepare it at 0.1 moles per liter. And then the conjugate base could come from a sodium acetate or a potassium acetate 0.1 molar solution to get AC minus. So these concentrations don't have to be the same as each other, but if the buffer is to be effective, to be efficient, they have to be no more than 10 times the conjugate. So 0.1 and 0.1, well, that's perfect. You could even go to 1 and 0.1, but that would be pushing the limits indeed. Now, I've drawn this picture, or maybe I've just grabbed it from somewhere, royalty free, which it is, and there are two lines of defense, and that is the key with buffers, is that you have two lines of defense. So let's take the glove to stop all the wrist shots which are coming from a strong acid. So they're going high, and the glove is made of acetate. So you can have H plus coming in, there it is, from hydrochloric acid or hydrobromic acid or whatever, so make it like a hockey puck, and it's shot up into the air, and then the goalie makes the save. And we cannot penetrate that little JPEG bubble there, but close enough. So the goalie makes the save and prevents the H plus from scoring a goal. Now a little bit of the leather on the glove is going to fray off a bit, and a reaction will have then H plus AC minus goes to form HAC. Okay, so the overall pH of the system will decrease, but it'll just decrease a bit. We aren't getting the H plus totally into the net. We're just getting it tiny bit closer to the goal line. Okay, so that's one line of defense. Now this glove has to be pretty big. If it's too small, then after 2 or 3 shots, wrist shots from the incoming acid, that glove is just going to weather away till nothing, and all sorts of goals are going to be scored. Same goes for a buffer. That conjugate base, that acetate, has to be a strong concentration to begin with. It has to have a large capacity to absorb the incoming acids. If you start with 0.00001 molar, then you just sneeze once. If you had some vinegar on your fries, so you're sneezing in some H+, and that ain't good. Your buffer's done. So you need a big glove in hockey, just like you need a big concentration for your acetate. Now, after a while, the defense, or through scouting reports, may heard, hey, this goalie, and you can choose whatever goalie you want from whatever team you want. You can decorate your goalie when you're sharing this analogy with others. So this goalie is great at stopping wrist shots. In other words, great at stopping incoming H pluses. So you have to find something else. What if we instead take screaming slap shots along the ground, along the base of the ice? And so you can think of sodium hydroxide releasing the OH minus, and that OH minus is going to be screaming in because maybe you heard that the goalie doesn't have good stick saves. Well, a good buffer, like a good goalie, will have more than one way to stop the puck. So the incoming hydroxide is coming in and it's going to hit the stick, and the goalie is going to make the save and resist a change in pH. If there is no strength in the stick save, then lots of goals are going to be scored. Lots of changes in pH are going to happen. But if you make good saves, if you have enough of the acid present, then you're going to make the save. So you're going to have, I'll put it over here, OH minus, the incoming strong base is going to be neutralized by the acid, and you're going to get H2O plus AC minus. So you do get a bit more of the conjugate base forming. Some of the acid does get consumed, but think of those as the splinters on the goalie stick that break off when you make the save. And yes, eventually the stick will be useless, but for a long time these stick saves will be good. And if you have a good balance between the stick saves and the wrist saves, you have a good balance in terms of neutralizing incoming base and incoming acid, and that is a very good thing. That is the two ways in which a buffer works to prevent large changes in pHs from happening. So I could get into the Henderson-Hasselbalch equation, or sometimes called the David Hasselhoff equation, but that would be the next step. Here, it was just the idea behind it. I hope you liked it. If some of my fellow YouTube superstars like Tyler DeWitt and Melissa Maribel, Professor Dave, and Khan Academy, if you like this, go ahead and use it. And but send me an email or a message telling me that you enjoyed this analogy. And I hope you all enjoyed it as well. Till next time.